All right, great. Let's get down to business then. So we have been talking about the natural logarithm. I want to say some more about that. Natural logarithm. Remember, we are discussing this in what I refer to as sort of a mathematically sophisticated way, somehow more sophisticated than probably how you learn this in high school, because it is based fundamentally on on calculus. The definition is the natural log of x is defined to be integral 1 to x of 1 over t dt. All right. This is not the way that you teach a kid what a logarithm means, because this is hard to understand if you don't already know calculus. But the idea is, if I want to know, for instance, like what is natural log of 2, it is this area. So the curve 1 over t looks like this. That's like 1 over x. And the natural log of 2, for example, if your little brother asks you, what does ln2 mean? It means that area, all right? This is actually not, like I said, not a good way to explain what ln2 means to a kid. It's probably better to say ln2 is some number where e to that number equals 2. But that kind of raises more questions than it answers. At least this does not raise any further questions. That's just what it is, and that's what it is, right? You don't have to go through any more definitions of any related concepts. And that's why, from an abstract point of view, this is actually a preferable definition to saying something about E, all right? Anyway, that was our definition. And we have been talking about various properties of the natural log. And all of these properties can be derived directly from the definition without thinking about E at all, because we are trying not to talk about E, at least for now. We will eventually talk about E. Well, like today, we'll talk about E. But anyway, the properties that we talked about last time, the first was that ln of 1 equals 0. Sorry, I wrote it the other way around. There was also the derivative of ln x is 1 over x. These things you absolutely should know. I would say memorize them, but I hope that you already know these things anyway. There was this property for multiplication inside of a log is the same as addition outside of the log. And then a similar one with quotients, natural log a over b, ln a minus ln b. You missed the huge, super important announcement. I'm not telling you now. I'll tell you after. Or your friends will tell you. All right, these are the properties that we discussed last time. I hope those are all familiar to you. These can be just derived using properties of E, but like I said, we are trying to do things the other way around. These can be derived just by using this definition of the natural log. All right, I think this is where we ended up last time, right? Let's discuss. There was one other sort of well, yeah, let's just go on. The last property, which for the sake of like using the natural log in real life, actually the last property may be the most important one. It is about the natural log of a power of something. For example, using the AB rule, log of AB, I can do something like this. What is the natural log of a squared? Well, if I think of a squared as AA, which is what it is, this is the same as natural log of a times a. But then I can do that rule, the log a plus log b rule on that. It's just a both times. We get ln a plus ln a. And that's, two of the same thing added together. So this we can write instead as 2 natural log of a, all right? The natural log of a squared is the same as 2 times the natural log of a. That is a rule about the second power here. Actually, this is not special about the number 2. If I had used a cubed, I could break this up as AAA, and then it'd be log a plus log a plus log a, and then you add them up. You would get 3 ln a, right? This is actually true for any exponent in there. And in fact, even exponents which are not whole numbers, something like the 1/2 power, this also works for that, although it's less obvious, but I'm just going to say it. So generally speaking, for any, I'll say for any x, we have this rule. Natural log of a to the x is x ln a. All right, this is a super important property of the natural log. And from the point of view of like solving equations using logs, this one is the really good one. This is extra useful if you're interested in solving equations. All right, we can use all of these rules together to simplify logs in interesting ways. So how about, and you'll see some homework problems about this, and these are pretty straightforward. Using the rules to simplify stuff. Or at least rewrite. I mean, it's debatable if this is any simpler, but for example, if I have the natural log of square root of x sine of x, let's try and rewrite this as much as we can using the rules up there. Anybody want to suggest how should I handle, we can do something with the square root. Yeah?
Like x sine x, like in parentheses to the 1/2.
Yeah, right. This is like what we almost always do with square roots in calculus. Write this instead as a 1/2 power. And then what can be done with that? Yeah?
Bring the 1/2 out.
Yeah, use the rule in the box there to, he says, bring the 1/2 out. I like that. 1/2 is like playing the role of x right here. So the 1/2 comes out front, and then what remains is x sine x. All right, can we do anything here? I see, yeah? Yeah, we have multiplication on the inside. It's x times sine of x. And so we can do the rule about multiplication on the inside. This one, right? Log of AB equals that stuff. So that's what I'm going to do. And I think this is more or less as simple as it's going to get. I'll just leave the 1/2 out there and then split up the log on the inside. It says ln x plus ln sine x. Great. And if you want, I guess you can distribute the 1/2 there. But this, now you can't continue any more of this business. You might wonder, can I do ln of sine x? Is that anything? The answer is no, not really. It's certainly not the same as sine of ln x. They don't do that. All right? So these rewriting using the log is sometimes helpful, although it's not precisely simplified. I mean, it's just a different way of writing it, which might be useful for some situations. All right? Great. Let's talk about ln x as a function and the graph of ln x. This is another case in which our definition is helpful in trying to talk about the graph. I will just remind us. The definition of ln x is this: integral 1 to x, 1 over t dt. All right. So, as far as the graph goes, actually there's sort of one special value that we already know. I'm going to try it maybe over here. I will try to draw the graph. Yeah, I'm not going to start drawing it yet. But anyway, we already know that ln of 1 equals 0, right? So that's one point that we can kind of mark off on the graph. And other values, I will draw the definition. Remember, the definition equals this kind of thing, right? The area here. There's 1, there's x. This area here is ln x, all right? And if you use x equal 1, then you get no area at all. That's why ln of 1 equals 0, all right? If I were to try and think about sort of the large-scale view of this area, one question you could ask is, what happens to this area if the x moves off to the right? Anyone want to say? Yeah? It approaches infinity, he said. Yeah, I think it's actually fairly obvious to see. Certainly, everyone would agree. If I move the x to the right, the area gets bigger, right? It doesn't get smaller. So that means my graph here, if I am going to graph ln x. I'm going to do it down here. Okay, so like here's 1. This graph is 0 right there, right? Because ln of 1 is 0. And what happens as the x gets bigger than 1? This area gets larger as the x increases. He said actually the area goes out to infinity, and that's true. So from here, I want to draw ln of x, which represents that area. It should get bigger as I go off to the right. And actually, it's not obvious the slope or whatever, but it looks something like that. The area gets bigger. And you can see the way I drew it, sort of the extent to which it's getting bigger is slowing down over time. That's because this area, it does continue to grow, but kind of not very quickly once you get over here, right? These areas, the area that you're adding on as you continue to move to the right is not all that much. So the increase of this line is not all that quickly. Although, I mean, closer to 1 it is more quickly. What about when the x goes sort of to the left? You know, I would like to continue the line over here. What if the x, maybe I used 1/2 here? What would you say about that area? Your choices are, does it continue to go down? Does it go back up somehow? If I move the x, certainly if I move the x all the way to this 1, there's no area. What if I back it up even further? Back that x up, as they say. What happens to the area then?
It shrink.
You are going to get some area. Like what is ln of 1/2, right? It would represent the area. Here's 1, here's 1/2. Like that, right? Yeah?
It would keep going down. So the line would keep going down.
This line would keep going down. Why do you say that?
Like an ln of 1/2, it's negative.
When you plug in, yeah, something you'll notice if you did this on your calculator, when you plug in ln of 1/2, actually it's negative. What, does that make any sense? I mean, it looks like I have some area here. Can anyone interpret why is that negative? Actually, it really is negative.
1, 0 goes below.
Yeah, it's because ln of 1/2, the definition of ln of 1/2 would be, sorry I'm a little crowded over here, it would be the integral from 1 to 1/2, 1 over t dt, right? That's the definition of the natural log. It's always from 1 to x. Now this one is from 1 to 1/2, which is the upside down boundary values, right? It means whatever the answer comes out, it'll be that area but negative, all right? And I would say, as this point continues to move towards the left, towards this y-axis, actually this area again becomes infinite here, all right? Only it's going to be counted as negative area because the boundary values are backwards. Okay, so when this curve continues into this region between 0 and 1, that area becomes, like I said, this area will again become infinite, only it's going to be negative this time. And so this actually sort of goes down here, asymptotically approaching the y-axis. All right, that's why the graph of the ln looks like this. And what about when the x is negative? Like what if you actually wanted to plug in some number back here? What is the log of that? Well, that would represent the natural log, say on, what about, I will say something about, how about something like ln of -1? Well, this would be the area under the curve from 1 all the way back to -1. And 1 over t, of course, it has another side here. That would be this and that. What is that?
0.
It's not 0. You might kind of feel like I have sort of two halves here. This is a positive half and this is a negative half, and they sort of add up and cancel each other out. But actually, we don't even count this at all as anything, because you can't do, so when you do an integral like this, it is part of the definition of the integral is that the function that goes in here has to be continuous from between 1 and x. And that is not the case right here. Yeah.
Is it a complex number?
this is a good question. Yeah, this is actually something you should always wonder when your math teacher says, oh no, you're not allowed to do that. This may be because you're just straight up not allowed to do that, or maybe because it's an imaginary number, like the square root of -1. At some point, your teachers are like, no, you can't do that. And then a few years later, they're like, actually, maybe you can do that. So whenever a mathematician says you can't do that, you should be a little suspicious. But the answer is basically this never equals anything. So it doesn't have a complex number as the answer. Although the natural log, when you're dealing with complex numbers, is actually kind of complicated. But as a one-liner, no, it's not a complex number. Although there's a little more to say about it than that, but I don't want to. So anyway, I would just say this integral here only makes sense if if the function right there is continuous between 1 and x. So if you go back here to the left, if you try and drive this x all the way back to the left, it doesn't even make any sense anymore. Which is why, so I will say this is bogus, because 1 over t isn't continuous on that part. I'll say 1 over t isn't continuous across this interval, right? As long as the x is positive, everything's fine. But once you make the x negative, the whole thing gets screwed up. And so, for that reason, ln of x is undefined when x is negative or 0. Right? You cannot do ln of a negative number. You also can't do ln of 0. All right. So anyway, this is the graph of the natural log. All right. So ln x looks like, I'll just draw it one more time. It only exists kind of on the right side of the y-axis. And it goes here at x equals 1 is the x-intercept of the natural log of x. All right? And maybe I will just say, so just based on this picture, what we've been saying, you can say some things about various limits. The lim as x goes to infinity of ln x is infinity. That is, if you look at this picture and continue to the right forever, this actually, it seems to be kind of slowing down in its growth. So you might think that at some point it reaches like a horizontal asymptote, but that's actually not true of the natural log. It continues to increase forever, and that's what I'm saying right here. This means there is no horizontal asymptote. It actually continues to go up forever. And going the other way, of course, you can never go past this line, but you can still talk about the lim as x approaches 0. And really it should be like that. This means the limit as x approaches 0 from the right side. That is to say, starting over here and approaching 0. It doesn't make sense to start over here and approach 0 from the other side. But this of ln x is negative infinity. That means it goes down forever as you approach the y-axis from the right. All right, those are some more basic properties of the natural log. All right, excellent. One thing to notice about this, and it's because of this first limit that I wrote here, these values, they go up forever, right? One thing that means is, if I look at y equals 1 here, there is some point, if I were to just kind of continue across, there is some number right there where so according to this picture, so there is some number x where ln of x equals 1. That's what I'm saying here. At some point, this curve actually does go through y equals 1. There's some number like right there. Right there is the number that I'm talking about. Anyone know what number that is? It's E, yeah, that's what E is. So this right here is our definition of the number E. So this is the definition. This is E with an exclamation point. All right, so from this point of view, we define the natural log first. And then what is the definition of E? I'm not going to use some weird limit of something to the nth power or whatever. The definition of E is just E is the number for which ln of E equals 1. All right? And another way of thinking about that, if you like, remember the definition of ln, it's this area under the curve, where that's 1, that's E, and the area equals 1. So E is sort of how far over to the right you need to go in order for that area down there to equal 1. I mean, eventually that area will equal 1, and then beyond there, it's always going to be bigger than 1. So there has to be like a specific point where that area eventually reaches the value of 1. And that specific point is what we call E. All right? That is the number E. And if you like, you can try to, like, E is sort of, it's an irrational number with a bunch of digits. It is, I don't have these digits memorized, but I wrote them down just for now. These are the first few digits of E. It's a number like pi where the digits go on forever without repeating or terminating. For some reason, pi is like cooler than E in the popular mind, I think. But ain't nothing wrong with E. All right. Any thoughts about that one? Here's a fun fact about E. I don't know if you're aware. E is a irrational number, right? And also pi is an irrational number. What that means that it never the digits never repeat. It also, another way of saying it is, it means that E can never be written as a fraction, like A divided by B, where A and B are whole numbers. That's what irrational number means. Anybody ever considered or thought about E plus pi? What do you think? Is that irrational or rational? Meaning if you took the digits, these are the digits of E, pi is 3.14, whatever. Add them together, which you could do, one digit at a time if you like. Do you expect this to be rational or irrational? Nobody has an opinion?
Probably irrational.
I think any reasonable person would say this ought to be irrational. It would be, in my opinion, it would be absurd if this ended up being rational. What that means is like somehow when you add these up, rational would mean maybe it does some stuff at the beginning, but after a while, like the digits always look like that, 1 every time or something like that. That couldn't possibly be true. E and pi are both essentially like random bunches of digits. When you add them up, you're going to get some other random bunch of digits. Anyway, the fun fact is actually everybody who you ask on the street will tell you, yeah, that's irrational, but actually this still has never been proven. And this is something that mathematicians are still working on. They got to work harder, in my opinion. It is not unknown if this is rational or not. That is in my opinion, ridiculous fact. This is something that, the people who work on this sort of thing this is in the research area called number theory. That is the part of mathematics which is about numbers. Of course, not all of math is about numbers, but the number theorists are working on that. I'm not a number theorist, so I don't feel badly saying it's ridiculous that we don't actually know what that is, but it's true. Any thoughts about that? Yeah.
I think they just put it in like AI.
So you could just try and can't you just plug these into your calculator and add them together? You can get a computer to calculate the digits of that number. The question though is, do these digits ever fall into a repeating pattern? And all the computer can answer is sort of, well, I calculated 1 million digits and they never repeated so far. But that doesn't mean actually that it's never going to repeat. And that's kind of the limits of using computers to do this. AI might be able to figure, like really what you need is some kind of logical proof that will somehow reason about all the digits simultaneously. And writing mathematical proofs is something that AI is still pretty bad at. So if you ask me, I mean, I haven't tried to do this, but AI will not have anything sensible to say about this anytime soon, at least. You probably found that already. Like even like ChatGPT is decent at doing simple math, but it's not very good at having original ideas about mathematics, in my experience. All right, great. Let's talk a little bit more. So I got some things about the natural log. Derivatives and integrals involving the natural log. Mostly derivatives for now. Derivatives and integrals using the natural log of x. All right, these are things, if you've taken a calculus course which used logs before, you probably are already familiar with this. The basic derivative rule, is the derivative of ln x is 1 over x. All right, that's the one we've talked about so far. Now, what if there's some other stuff on the inside of the function? If there's, say, more stuff inside, not just x, like if it was instead of just x, maybe, I don't know, something else in there, some other function, ln of g of x, that means just some other function also plugged in there. How would we handle the derivative of that? Well, this is the standard scenario for using the chain rule. That's what you do when you have a function on the outside and a function on the inside. And I hope everybody remembers. The way to do the chain rule, you take the derivative of the outside part, leaving the inside the same, and then you multiply separately by the derivative of the inside part. So here, I'm going to do the chain rule. Chain rule. And I begin with the derivative of the outside part. The outside part is the ln, so it's going to be 1 over g of x. This right here is the derivative of the outside part with the same thing on the inside. All right? Now the derivative of ln of x is 1 over x. Derivative of ln g of x will be 1 over g of x with the same thing on the inside. That's why I didn't change the g. And then separately we multiply times the derivative of the inside, and that I would just write as g prime of x. All right? So this is the derivative of a log with some other stuff on the inside. And sometimes, like if you look up, our book has this formula written down somewhere. You can, of course, write that as one whole fraction. So if you like, this actually is not really a formula which I have memorized, but some people like to remember formulas like this, and you can if you want to. These two formulas in the boxes are really the same thing. It's just like this one is using the chain rule also. Now, if you ask me, like, I have the top one memorized, absolutely. I don't really the bottom one. If I have to use something like the bottom one, I just do the top one and do the chain rule. So it's it's up to you how you want to remember these formulas. The one on the top you absolutely must know. The one on the bottom you can remember if you like, or you can just remember when I got some stuff on the inside, I got to do the chain rule. All right, let's just try a few examples here, and then I have some for you to try. These are just going to be derivatives of ln of something or other. All right. So when I see ln of something, the derivative is 1 over that same stuff. So it's going to be 1 over x squared plus 5x minus 1. And then separately times the derivative of the inside. Anyone want to say what's the derivative of the inside here? 2x plus 5. Great. And if you're going to write it over here, you better put parentheses around it, like so. All right. If you don't put those parentheses, then you're only multiplying 5 times 2x, which is not what you mean. All right. That's a straightforward one. I got 2 more. These really aren't going to get all that complicated. All right. I got log of root 3x minus 5. I would suggest, as we always do, write the square root as a 1/2 power. So this is ln, and then I'm going to write, not there, 1/2 power. So 3x minus 5 to the 1/2, like that. All right? And now I'm going to do the chain rule. And this actually requires using the chain rule twice. But we don't have to worry about that until we get there. The derivative of a log of something is always 1 over that something. So this is 1 over 3x minus 5 to the 1/2, like so. And now I go times the derivative of the inside. And the inside of the log is all of that, including the 1/2 power. So what's the derivative of this? For that, we need the chain rule. Again, I would move the power down first, and then write the same thing on the inside, and then multiply by the derivative of the very innermost inside. So I'd go 1/2 here, 3x minus 5 to the minus half. That's the derivative of the 1/2 power on this part. And then I have to do the chain rule one final time to get the derivative of the very any inside, which is just 3, like that. All right. Having done this, you could simplify it if you want to, but I don't really suggest that. Yeah?
Could you just move the 1/2 in front of the natural log to begin?
Yeah, so this is actually, you can use one of our rules about the log to make this a little simpler maybe. So here's an alternative way of doing this, which I was going to say. Instead of, so you would still write the 1/2 power. But then what she said is move the 1/2 exponent out to the front, because that's one of our properties of the log. So this you can write as derivative of 1/2 ln 3x minus 5, right? Now this 1/2 is just a number coefficient, so it is unaffected by the derivative, and then the derivative of this stuff is whatever it is. So the 1/2 will just stay like it is. That's a coefficient. And then the derivative of the log part is 1 over 3x minus 5 times 3, like that. So this is another way of doing the derivative. And these, they look kind of different, but they are actually the same. Because this minus 1/2 power, you could write inside this denominator, and these two 1/2s would combine and give you just a 1 power. So that really is the same as this, even though on the surface they don't look exactly the same. Right? You can always use your rules for the logs to make things easier. All right. One more. This is actually very simple looking. What is the derivative of ln of negative x? You cannot just factor the minus sign out of the log. That's not one of our rules. So we should just use the chain rule here. The derivative of that is 1 over negative x times the derivative of the inside, which is minus 1, right? This is actually a simpler example than those ones that we did up there. But this is interesting because the answer here, if I simplify, just the minus signs will cancel out. This is just 1 over x, right? And what's interesting about that is, so, derivative of ln x is the same as derivative of ln of minus x. And what that means is these two functions, or it means when you take the derivative of a log, it actually doesn't matter what the sign of the number on the inside is. It could be either way, right? The fact that there's a minus sign in here or not actually has no effect on anything. You get the same answer anyways. It's 1 over x. Okay, so we can say the sign on the inside doesn't matter. This is a somewhat weird looking formula, like so. No matter what the sign is of the x, you just make it positive, and its derivative is still equal to 1 over x. All right? The natural log of the absolute value x is 1 over x. That's because, like, why are we allowed to insert absolute values in here? It's because of what I just said. It doesn't matter what the sign of that thing is on the inside. And so either way, you will get the derivative of that ln of either x or minus x is 1 over x. All right. This is important because what this function over here, ln of absolute value x, is something that you can actually plug negative numbers into, and everything will work out. Because if I plug in x equals -2, the absolute values make it positive first, and then you really can do the natural log. So anyway, that is important because this gives us an integration formula, or an antiderivative. Integral 1 over x dx is ln of absolute value x plus c. I just wrote this. This is a derivative formula. I wrote it the other way around to make it an integral formula. If the derivative of the log of absolute value x is 1 over x, that means the integral of 1 over x is log of absolute value x plus c. And this is the basic antiderivative or integral formula involving the log. I'm not telling you what is the integral of the log. Actually, that's something else entirely. But this is the integral of something gives you a log, all right? A natural log, of course. All right, this antiderivative formula is actually quite useful. So I've just got one last thing, and then I have some for you all to try. So this antiderivative formula actually does come up fairly often. This is especially useful with u substitutions. For example, if I wanted to do something like that. So the standard scenario when you want to do u substitution is when you have like a thing on the inside of parentheses usually, although I don't see anything like that here. We still have to choose the u to be something. Anybody got a suggestion? There isn't really an inside of anything, but yeah. Yeah, I suppose you have two choices, right? You could choose the 3x or you could choose the 4 minus x squared. It turns out in examples like this, you want to choose the denominator to be the u. So I will just say sometimes, of course this is not a hard and fast rule, but make u equal the denominator. We will see in this example it's going to work out. All right, to do the rest of the substitution, I would now find the du, which is -2x dx. And maybe I'll divide the -2 like I usually do. -1/2 du equals x times dx. All right. And now I'm going to try to rewrite what I see on the inside of the integral. As usual, I'll write this in a few steps, but if you can tell what's going to happen, you can probably skip some of these steps. All right. 3x over u times dx. Right? I just put the u where it goes. Now, what can we do with 3x? I would say we can move the 3 out of the integral, first of all, because that's a constant multiple. And then x on the top, we can sort of group that together with the dx. So I'm going to write this as 3 integral 1 over u and then x and dx. All right. So this 3 just went outside. This x came over and I wrote next to the dx. And then x dx is equal to -1/2 du. So this is going to be 3 1 over u times -1/2 du, like so. And then this -1/2 being a constant can come all the way out. And then finally, I think I will be ready to do this integral. Like that, right? -3/2 integral 1 over u. And how do we do integral 1 over u? That's the formula that I just said. It's this, right? Integral 1 over x dx is ln of absolute value of x. So right here, this constant out front stays like it is. The antiderivative is that, ln of absolute value of u. And then the very last step, as always, put the x's back in. So my final answer shall be ln absolute value 4 minus x squared. Like that. All right. Any thoughts about that? Anybody, maybe I can say one little thing. Like I got some for you all to try, but at this point right here, was anyone thinking, couldn't I just do this and then do the power thing with that? Write it as a minus one power. There's a problem with that theory. Anybody have a problem with that? Yeah, if you were going to do the power thing, okay, that means you increase the power by 1, and it becomes, so the power rule here would say I increase the power by 1, it becomes u to the 0. Actually, this by itself is not so much of a problem. What's the problem? Well, this would be the antiderivative of that, because I increase the power by 1. But I mean, u to the 0, that's okay. Like that equals 1, right? There's something else wrong about this. Yeah, it's because you would also have to do this, right? You divide by the new exponent in the front, and that is not allowed. This is bogus. All right. So when you see integral of something to the minus 1 power, don't try to do the power rule. You'll end up with this, and then you'll be puzzled. What am I supposed to do with 1 over 0, u to the 0? The answer is you're not supposed to do that at all. You're supposed to write ln of absolute value u instead. That's the appropriate rule to do here. So if you ever see this and find yourself wondering, I don't like the looks of that. That is a good impulse. It's the natural log instead. It means you forgot that you were supposed to use the natural log in this situation. All right. Okay, great. I got some for you all to try. These are just 2 integrals which involve the u substitution similarly into this way that I just did. Both of these are somewhat weird. Maybe I'll write tanks. This is just the integral of tangent. It doesn't look like much, maybe some of you have this memorized. I don't know. But would anyone like to suggest the very first step? We have to rewrite this in a maybe make it look a little bit more complicated, just so that you have something to work with. Right? As written, we don't have anything to work with at all. Anyone remember a way to rewrite the tangent in a helpful way? Huh? Yeah, write this as sine over cosine, and then that'll get you going. And then I got another one here. Try that other one too.
This is good. This one is after
This multiplication right here, you can just do that.
Because I thought it was like, that's the same, oh no, it's only if this was a plus sign, it can be separated.
And it's weird that this is an x, but this.
Yeah.
So you need to choose this differently.
Just that one, that's what we do.
Yeah, that's great. Let's chat about these. Sorry I didn't get to you guys in the middle. I hope you're doing okay without me. I will next time. The first one, tan of x. This, as they said, you should start by writing sine over cosine. I saw most folks work this one out just fine. And then I would like to choose the denominator as the u here. And then the du is minus sine x dx. All right? This is the u and the du for that one. So when I plug stuff in, it'll say sine x over u dx, and writing it slightly differently, 1 over u sine of x dx. And then because I have sine of x and dx, that matches here. Actually, with a minus sign over here, this is negative du. So this would be integral 1 over u times negative du. And then we can factor this negative sign all the way out front. Minus integral 1 over u du. And then that is minus ln absolute value u plus c, like that. This is the integral of tangent. I do not suggest that you memorize this, although I guess some people know this formula. Any questions about that? This is an interesting example in my opinion. This is an example where the natural log just kind of comes out of nowhere. Like in the original formulation here, this is just a tangent by itself, doesn't have anything to do with the natural log. Sometimes I wonder about, like, if you could show this to Archimedes, he would be very interested because he knew about sine and cosine and tangent. But to him, these were all things related to circles and triangles. They had nothing to do with the natural log. Like those guys who invented sine and cosine and tan had no concept of the natural log. And from a modern point of view, I would say sine, cosine, and tangent, like the entire enterprise of trigonometry, is completely different from the historical origins of the natural log, which, like, logs and the number e, those things all became interesting to people who were studying exponential growth, and in particular, like, compounding interest. Like the natural log and e to the x, those are like properties of modern capitalism. That's why people became interested in those mathematically. Whereas the trig functions are like thousands of years old, and people invented those for completely different reasons. But it turns out there's actually, like, they are mixed up in unexpected ways. Very strange, in my opinion. This is one of the things that people are interested in, mathematically speaking. Weird connections that nobody would have expected. Anyway, this one here, let's do this with a u substitution. Here you basically have two choices. You could pick the x, which is in the denominator, or you could choose ln of x. Now, I gave you a bit of misdirection, perhaps. Usually you do want to choose the denominator to be the u, but in this example, actually, that doesn't do anything. Maybe I will just, for a moment, don't write this down because this isn't going anywhere, but if you tried to do this, you would have said u equals x, du equals dx, and then when you go to substitute, you just, okay, x and u are the same, so this would say ln of u, and then dx and du are the same, so this would be du over here. And you'll notice, like, okay, I did the substitution, but I end up with exactly the thing that I started with. Like, it's actually a fact, u equals x is never a helpful substitution. There is no situation in which this works, because if you do the substitution correctly, all you're going to do is get the same thing you started with. You will have made no progress. Congratulations, you played yourself, as they say. So I'm not going to do that. I am instead going to choose the other one. Then the du is 1 over x dx. And now actually things kind of line up nicely. If you separate this apart a little bit, it says I can write it as ln x times 1 over x dx. ln x is u, 1 over x dx is du. So this is the same as integral u du, and that we can just do the power rule. This is u to the power 1, so the integral is 1/2 u to the squared plus c. 1/2 ln, actually we don't need the absolute values here, like that, plus not equal. All right, like that. I hope that's what you all got. Any thoughts about that one? How about this? Can the 2 come down here and cancel the 1/2? No, you don't do that. The rule about exponents would be like this. If the 2 was inside the parentheses like that, then you can bring it up, but not when it's like this. You really can't do anything to simplify that. All right, great. Any questions about that one? People seem to be doing just fine with that one. All right, we got some time left. Let's try one last thing to say about the natural log, and then we're going to talk about ease in more detail. One last thing to say about the natural log. We can use our ln properties to do derivatives. I will say some derivatives easily, in quotes. I'll put this in quotes. It's a somewhat weird trick that you can use the natural log properties to do some derivatives easily, in quotes. I'll leave it up to you to decide if this is actually easier or not, or harder than doing it kind of without this trick. But this is referred to as logarithmic differentiation. And you will see some of these on the homework. They'll give you a function and say, find the derivative using a logarithmic differentiation. So here's what that means. For example, I'll just try one example here, and then I have one for you to try, and maybe that'll do it for today. I don't know. Let's say I have this function, x squared 7 plus x to the 10 divided by 5x squared minus 7x plus 4. And your job, find dy dx, the derivative. All right. So if you don't use logarithmic differentiation, you still can do this one. It involves using the quotient rule and the product rule and the chain rule like several times. Here we have what is basically overall a quotient because of this big bar, but you'll notice inside the top there's also a product here. And then this 10th power means you'll have to do some chain rule business for that, all right? So you can do this by just some combination of product, quotient, and chain rules. But instead, I'm going to show you how to do what they call logarithmic differentiation, all right? So the logarithmic differentiation is you take ln on both sides. This is a little weird if you've never seen it before, but I mean, it's not especially hard to do, but you sort of got to know how to do it. You take the natural log on both sides, and then do the derivative. And I'm going to say, then you do what we call the implicit derivative, which I hope you've seen before, but this is going to be a very easy example of it, so even if you haven't heard of that, it'll be fine. So you're going to take the log on both sides, and then do implicit derivative. Here's what it looks like. First of all, take the log on both sides. ln y, and on the right, ln of all of that business. Okay, and then do the implicit derivative. Actually, I'm not going to do the derivative immediately because we can simplify the thing on the right. See, what makes this a pain to deal with in the derivative is all these products and quotients. So I'm going to try to rewrite this thing and this 10th power, right? I'm going to try to rewrite this thing with no products or quotients or 10th powers. That's the idea. And we do so by using our rules of the log. Can anyone say what's like the first rule of the log we should use? Yeah, the subtraction rule. Because this overall looks like a quotient, I can write this using a subtraction instead. This is how the logarithmic differentiation trick avoids the quotient rule. That's the whole purpose of this. Instead, I'm going to do that sort of quotient type property of the log, which is this kind of subtraction rule, right? And when I write it that way, I no longer need to do the quotient rule because it's not a quotient anymore. It's just two things subtracted from one another. All right, actually we can continue to simplify. The first one, anyone have a suggestion? I can rewrite the first one there. So I'm still not going to do the derivative yet. Yeah?
It'd be ln x squared plus ln 7 plus x to the 10, and then minus.
Yeah, right. So this one has multiplication right here, right? X squared times the other thing. And we can split it apart as the log of x squared and then also the log of 7 plus x to the 10 minus. Can you do the same thing here? The answer is no. These are already added together on the inside, and there is no such rule about log of a plus b equals whatever. That's just, you can't do anything with that. So this, you got to leave like it is. 5x squared minus 7x plus 4, like that. All right, can we do any more? Yeah, what else?
The first one turned to 2 ln of x.
Yes, the first one we can move the 2 into the front, 2 ln x. That's not getting any simpler than that. The next one, actually, we can do the same thing with the 10th power. 10 ln 7 plus x. And this part at the end, you just got to leave like it is. All right, so we have now rewritten the thing so that it has no products or quotients. Now, taking the derivative on both sides is very easy. You don't need to use the product or the quotient rule at all. In fact, you could live your whole life never learning the product or quotient rules. Always do it this way. I don't recommend that really, but this is an alternative to the product rule. Is turn it into logs, and then instead of products, it's added. And then you don't need a rule for addition. All right, anyway, now I'm going to do the derivative. And the implicit derivative means you just take the derivative on both sides of everything. So now I'm going to do the derivative on both sides. On the left, ln y becomes 1 over y dy dx. And this is called the implicit derivative. It means when you take the derivative of something involving a y, you have to multiply times dy dx. If you like, you could think of this as the chain rule, because the derivative of ln y would just be 1 over y, but then I have to multiply times the derivative of the inside, which is that. That is the derivative of the inside, all right? And then the right-hand side, I take the derivative of all of those. Each one is just 1 over whatever. So the 2 ln x, the 2 stays like it is, but it's 2 times 1 over x. And then the 10 whatever, the 10 stays like it is, and then it's 1 over 7 plus x. Now we do need to use the chain rule here, but the derivative, like the derivative of the inside here, derivative 7 plus x is just 1, so it doesn't really matter in this one. It is going to matter in this one. The last one will be minus 1 over this business, and then chain rule says I multiply times the derivative of the inside, which is 10x minus 7 in this case. All right, that's the derivative on both sides. And then finally, we solve for dy dx, and that's our final answer. So we solve for dy dx, which is easy. We just have to multiply both sides by y. So this will say dy dx equals y times, can I just say this, all of this stuff? Now that's the answer, but you should really write your answer in terms of x's. Not here, what we have is a mixture of y's and x's. I have a y over there and then a bunch of x's. Any implicit derivative fans out there? Do you remember what to do with this? I want to write it all in x's, not some mixture of y's and x's. Yeah?
You just go back to the top, take y equals the same as
Yeah, right. Go back to the top. This is what y is in terms of x. So stick that in for y at the very end. So my final answer is x squared 7 plus x to the 10 over 5x squared minus 7x plus 4 times, and I'm going to write this other stuff out. 2 over x, I just put stuff into the numerators of these fractions, plus 10 over 7 plus x minus 10x minus 7 over 5x squared minus 7x plus 4. There you go. This is the derivative. And that's my final answer. This is the logarithmic differentiation trick. Now, I said this is easier than the product rule or the quotient rule. And then it took me like 15 minutes to do the whole thing. This is why I said it's a little debatable whether this is actually easier or not. And I sort of, I put it in quotes here. You can do these derivatives easily, right? Although it took me a while. But I would like for you, let's just sort of like take a step back and take a good hard look. If you know what you're doing, you can basically, you start with this, right? If you know what you're doing, I think you can more or less entirely in your head jump down to here. From there to there, almost nothing happened. It's just I did all the rules with the logs. So every multiplication turned into an addition, and every exponent turned into a coefficient, and every division turned into a subtraction, right? All of that is actually very easy to just do all in your head if you are used to doing this trick. And then what about the derivatives? I mean, these derivatives are all easy. That's the whole point of this, is so that you can do this easy step rather than doing the product and the quotient rule. And then to go from here to here is just a matter of basically rewriting stuff. So I don't know if this seems especially easy to you, but once you get in the rhythm of it, it actually is a fairly nice way to work out derivatives from time to time. All right, I got one for you to try, and that'll do us for today. See what you think. Of course, when you're doing these on your homework or whatever, you can write out as many steps as you like. Take the derivative. Try it out. People seem to be doing fine. These ones, I think once you get the hang of it, it'll maybe take you a little while to write it down, but it's very simple, like the individual steps are not very complicated. So I would start by breaking up the quotient into this. Here's one way that you might mess it up if you are trying to do many steps at once, which is usually I have no problem with. ln x to the 4 is 4 ln x. This one here is a minus, and then it will split into this one plus this one, but this minus on the outside really means it's minus, it's like this, ln of this one plus ln of this one. That minus needs to distribute. So really, once you get it sort of all the way broken down, it should look like minus ln 2x minus 1 minus the exponent of 5 can come out, ln 3x squared minus 7x. Make sure you have a minus here also. If you try to do too many steps in your head, you might have failed to distribute the minus sign right there. But anyway, this is, all of this equals ln y on the left. Right? And so I'm going to take the derivative. It will say 1 over y dy dx. And then this business becomes 4 over x minus 2 over 2x minus 1. I'm doing a few steps in my head, but this is the chain rule, right? I put this in the denominator and then multiply times the derivative of the inside, which is 2. And then this one will be minus 5, and then 6x minus 7 over, like that. And I forgot to write my, no, that's good. Am I doing all right? I think that's right. And then just multiply everything by y. Would you mind if I do this? Scribbly scribble. And then put y right here, which is my original formula. X to the 4 over that business. It really is easy. It's just you have to know what you're doing and not make any little mistakes.